Hello. From the last lecture, we started to consider regression models with multiple regressors. One of the important motivations to have multiple regressors is that if you do not include relevant variables, then the omission can cause some bias, some misleading result. And that's called the omission variable bias. And in our example, we wanted to study the effect of student-to-teacher ratio to the test scores, but we used the percentage of English learners as an omitted variable. And what we considered there is an indirect channel from student-to-teacher ratio to the test score through the percentage of English learners. That is the indirect channel, which is not what we are interested in. So we wanted to estimate the direct effect of student-to-teacher ratio on test scores. Because, so for example, if you are the superintendent, hiring more students does not change the percentage of English learners in your school district. So changing the indirect channel is not what I want. But the problem here is because you do not observe or you did not include that relevant variable in the regression model, so the indirect channel is absorbed into your estimate, and your estimate may be overestimated or underestimated. In our case, we guessed the direction, and what we thought here in that example was that if the student-to-teacher ratio is high, so higher student-to-teacher ratio means the school district is less is more likely to be less affluent. Then may be associated with higher immigrants families, and then may result in higher percentage of English learners, and because they are non-native speakers in English, so their test scores will be lower. So this is an indirect channel that is not what you want, but that is included in your estimate, even if you did not want it. So then the solution is, in the conclusion, the solution is include that variable. To include that variable, that then you make a regression model with two regressors. So using the same idea, you may extend the number of regressors to any arbitrary number, but let's consider two regressor case. So two regressor case can be written in this way. With single regressor case, ith observation of y equals an intercept beta 0 plus slope beta 1 x1I. So that and plus error term was the regression model for one regressor case. However, now you have x2. So you can think x1 as student-to-teacher ratio and x2 as the percentage of English learners. So two variables determine y at the same time. So you have simple linear relationship using different slopes. Different slopes indicate different effects from each variable. And the terms are pretty much the same. Y, the left-hand side variable, y is the dependent variable or the outcome variable, left-hand side variable, y variable, and because it is determined by the other guys. And x1 and x2 are independent variables or regressors, right-hand side variables, explanatory variables. There are many different names, but maybe I'm going to use regressor or independent variable or explanatory variable. I think those terms are pretty self-evident. And we observe three characteristics from the same observation, from the same observational unit. So, for example, in our example, from one school district, we observe the test score, the student-to-teacher ratio, and the percentage of English learners at the same time. So you have to have observed these three at the same time. And the interpretation of the parameters, beta 0 is the intercept, which is the same as before, and beta 1 and beta 2 are the effect of their respective variable on the outcome variable. But there is an additional condition. You have to fix the other variable constant. So the other variable does not change, but you are changing only one variable in the regression model. And finally, the error term is the error term, but you may think it as other omitted factors. Still, it is impossible to include all the possible determinants into the regression, maybe because of the lack of data, or you may not have enough computing power. And just you may ignore minor things in this setup. So anyhow, all the other things are collected in the error term. And then now what we are going to do here is to understand what happens in beta 1. We will have a hypothetical experiment. Suppose that your student-to-teacher ratio, x1, student-to-teacher ratio is now at a point x10. So like, let's say your student-to-teacher ratio is now 10, say. But so your expected value of test score, you can expect test score y as much as this. So error term is removed because its expectation is 0. The error term is expectedly 0 on average. So your test score, expectation of the test score depends only on your student-to-teacher ratio and the percentage of English learners in your school. That's how you can form your expectation. And now think about a change. Suppose that your student-to-teacher ratio was 10, but your budget is not enough. So you realize your budget was cut, and you had to increase the student-to-teacher ratio to, say, 11 or 12. So delta x1 is the change in the student-to-teacher ratio. But the percentage of English learners has not been changed yet because it is not affected by x1 in this situation. And then because of this, you have to adjust the expectation of the test score. So the test score expectation will be changed by delta y. So delta y captures the change in the expectation of test score, and delta x1 captures the change in the student-to-teacher ratio. And then by comparing these two, you can calculate the expected change in the test score caused by the change in x1. That's simple. So before, you have this expectation, and after the change, you have this. So by subtracting the before equation from the after equation, then you get delta y equals beta 1 delta x1. So it's simple. It's easy to define. Now it's easy to define what's beta 1. So beta 1 is something like differentiation. So when x1 changes by delta x1, y changes delta y, holding x2 constant. As you can see, x2 was held fixed, so it's constant. And then beta 1 captures the effect of x1 on y. So when you increase when you increase the student to teacher ratio by 1 unit, then the expected test score increases by beta 1. So usually we think beta 1 will be negative. Anyhow, it's an like negative increase is decrease. So beta 1 is defined this way, which is clear from our definition, and you have to realize, you have to notice that there is a additional condition, ceteris paribus assumption, and beta 0. Beta 0, in a similar way as in the single regressor case, beta 0 must be the predicted value of y, expected value of test score, when both variables disappear. So both variables are 0. So if x1 is 0 and x2 is 0, then beta 1 and beta 2 will disappear, and you only get beta 0. So that is the interpretation of beta 0, which is the intercept. And beta 2 is defined symmetrically as beta 1. Okay, so this is a brief setup and terminology for multiple regressor case. And as you see, it's straightforward extension of single regressor case. So I want you to think it as a review of the previous chapter, and like so it will help. I believe it helps to helps you better understand what happened in the earlier chapter. So I will continue in the next video, and see you again.